My experience is that most theorists don't talk to experimentalists, and most experimentalists don't talk to theorists. And I've also had the experience of going to the experimental leadership and saying, "Hey, I want to look for this new weird thing," and having them say to me, "Well, there's no theory paper on that idea." So I know, but we have the idea. They're like, "Well, there's no theory paper on it, so you can't do it." So then we go and write the theory paper with the theorists, and then I can come back and say, "Okay, now we have a theory paper. Can we do this?" And they say, "Okay, yes."
The guest of today's podcast is Dr. Daniel Whiteson. He is an experimental high energy physicist at UC Irvine, and he works in the Atlas collaboration, which is one of the collaborations in the LHC. He is also a science communicator who made the Daytime Emmy nominated series Elinor Wonders Why, and he also hosts a podcast named Daniel and Kelly's Extraordinary Universe. So let's welcome Dr. Whiteson on the podcast and listen to what he has to say. So, Dr. Whiteson, welcome to the podcast. It's nice to have
Thanks,
you.
sir. Thanks very much for having me on. It's fun to be here.
So before we talk about anything else, can you tell me about how how you got interested into physics, as a young person?
Oh, yeah. That's not that inspirational a story, unfortunately. I grew up in Los Alamos in New Mexico, so home of the Manhattan Project and the National Lab. My parents worked at the lab, and my high school physics teacher was a physicist at the lab. And so physics was just sort of everywhere. And it was the thing everybody said was the hardest thing to do. And so I didn't know what I wanted to do with myself. So I thought, well, I'll just try the hardest thing. And then if they say no, then I'll try the next hardest thing. And 30 years later, here I am still doing physics. It actually took me a little while before I discovered my own actual interest in physics, my own like personal passion for physics. So I was doing physics for years before I actually was motivated to do it. I tried lots of different kinds of physics, laser physics, plasma physics, found them all a little bit boring in terms of the day-to-day work. And it wasn't until I tried particle physics one summer that I realized, oh my gosh, this can actually be fun. There can be a part of it that gets you really excited and you can work on fun puzzles and answer questions that you think are exciting. So it took me years to actually connect, like in a sincere way, with the physics I was doing.
So you said that when you were in Los Alamos, people around you were telling you that physics is the hardest thing to do. So were there any particularly not famous figures that were around you that were telling you this thing? Because I assume that Los Alamos invites a lot of very well-known physicists.
I'm sure there were lots of well-known physicists in Los Alamos. I wasn't hanging out with any of them. I was just, growing up in this environment. It's a competitive high school, and everybody's parents have PhDs, and sort of academically very ambitious. And so everybody's sort of pushed to do the most challenging thing, do the most you can. Um, and so I didn't get to hang out with any famous physicists in Los Alamos when I was a teenager, unfortunately. But I was really grateful that the guy who was teaching our AP physics class, I mean, he was a physicist. He would get up at 6 in the morning, come teach AP physics at the high school, and then go to work all day as a physicist. He was a fabulous teacher. And so shout out to all the high school physics teachers out there, or all the high school teachers in general, who are really like serving on the front lines of our society, inspiring kids and changing the direction of their lives.
Right. So you said that when you learn more about particle physics, then you discovered that, okay, this is something that you really like to do. So
Mhm.
how did you come into contact with particle physics, for the first time?
I took a class on particle physics as a junior, as an undergrad, and that's when I realized, oh my gosh, I am desperate to know the answer to these questions. Like, I took electromagnetism and I took thermodynamics, and sure, there were fun puzzles to work on homework with. But when we were doing particle physics, I just always wanted to know more. How does isospin work? What is this thing? Where does it come from? Why does it work at all? It just really connected with me in a personal way. And I didn't realize until then that that's how most of science is or should be, that everybody's working on questions they personally find exciting. The guys who are staying up all night in the Amazon rainforest to watch some weird kind of beetle have sex in the trees, they're doing that because they're super curious about how beetles reproduce, right? It's their
Right.
passion. They chose that question instead of, how do galaxies form or whatever. And science is all about people choosing their individual questions. And when I took that class in particle physics from Hanu Miettinen at Rice, I was like, oh my gosh, these are fascinating questions. I desperately want to know the answers to. It really connected me with it personally in a way I had never experienced before.
Right. Okay. So you work in the Atlas collaboration, which is one of
Mhm.
the collaborations in the Large Hadron Collider, and I'm pretty sure that there are multiple projects that Atlas collaboration has done over the years. So what are the projects that you are most indulged in right now in the Atlas collaboration?
Yeah, Atlas is a huge collaboration, like thousands of people. So you're right, there's a lot going on. And, there's a lot going on that's sort of your bread and butter LHC experimental physics. Let's measure the Higgs to great precision and see if it's the Higgs that we thought it was, or if it's some new weird kind of Higgs. And that's important work, and it's got to be done. And hopefully, it will reveal some new physics, et cetera, et cetera. It's not the kind of thing that really gets me going in the morning, because there's not as much room there for creativity as there is in other areas. I prefer to work on things that are a little bit more off the beaten path, where people haven't for 10 years already figured out what the strategy is for doing it. And so, something I'm really excited about at the LHC is opening up the possibility for single event discovery. Like most of the discoveries we make at the Large Hadron Collider are statistical. You see a pile of events over some background, and you're like, oh, this is 3 sigma or 5 sigma, um, not a fluctuation, right? And that's cool. And the Higgs was discovered that way, the top was discovered that way, and that's great. But I miss the days before I was in particle physics and before you were in particle physics when you could discover things with a single event. You could see a collision and trace the particles that came out, and you're like, this is something new. The way like the positron was discovered. It's a single event. Discovery, Nobel Prize. That's what I want. I want something fascinating and indisputably new. And I think it's possible at the LHC. And I'm working on a project that I hope might actually lead to a single event discovery. And that's looking for new kinds of really weird tracks, particles that move in the magnetic field in ways unlike simple electromagnetically charged particles.
That's interesting because the examples that you were giving, the example of the positron or the muon, these were single event discoveries. But something like Large Hadron Collider, which smashes protons together, which are made up of quarks, so it can be very messy. So how can a single event give us some discovery with confidence? I mean, that's a bit counterintuitive to me.
Yeah, exactly. And that's what makes it exciting to me, because it means nobody's looking, which means that the data could still be there right now, waiting for us to make this discovery. So you ask a great question. How is it possible to make a single event discovery at the Large Hadron Collider? It's such a messy environment. But we produce these tracks and we have these very high fidelity detectors that trace the path of the particles. And we can reconstruct those paths. And say I show you an event and it's got, a bunch of hits in an obvious path, but that path is not a helix, right? Electromagnetically charged particles move in as a helix in a magnetic field. But what if I show you something that's not a helix and it's clearly a path of a particle? That's something new right there. Well, I don't know what it is. I don't have a
Right.
theory to explain it, but it's something new. And there are some theories of particles like this. Now, in my view, we don't need a theory to motivate a search. We don't need to know what something is going to be in advance in order to look for it. But just as a, example to help think about this more concretely, there are theories of particles called quirks, not quarks, right? Quirks. Quirks are particles that are charged under some new kind of strong force. Some strong force, but these quirks are so but the confinement scale for the strong force is is different so that these things actually stay macroscopically separated. They don't create showers. And so they oscillate in the detector in weird ways that are not helices. So the challenge is, can we look for things that are not helices in the Atlas volume? Because all of our tracking software is designed only to very efficiently, very quickly, very effectively find helices, and it never even looks for anything else.
Right. Okay. But how would so the thing is that I'm still not able to understand that if you even if you are looking for something like quirks, then why do you have to do it with a single event discovery?
I suppose you don't have to, but it's exciting that you could, right? These things
Okay.
could be very rare. And so all you would need is one event. Because the tracker is so high resolution, it gives you like a picture of the event in a way that provides almost a background free signal. So you could discover quirks as an excess over the background statistically in some one-dimensional feature, sure. But it's exciting to think about how you could make a single event discovery. Absolutely.
Right. It may be a very basic question because I'm not an experimental physicist, but how would you distinguish, a single event that, suggests some new thing from an artifact or a statistical fluctuation? Can you
No,
do
it's a
that?
great point. It's a great point because in reality, there is no background free discovery, right? There's always some chance that you're being fooled. I mean, the example people like to give is looking for a unicorn or Bigfoot, right? And saying, hey, it might be hard to find the unicorn, but once you found the unicorn, nobody doubts you have a unicorn. Well, it's not exactly true. I mean, you could get fooled, and there are pictures of Bigfoot, they're not really Bigfoot, etc. So you always have to consider the fact that there could be something that mimics your signal, right? There could be some random chance, maybe a bunch of random noise in the detector that looks like it. And so you got to do your due diligence. You got to calculate those backgrounds. You can never just say, here, look at my picture. Obviously, this is something new. You have to have a calculation that shows that it's very unlikely to be due to chance or due to any other kind of background. Um, so, it's never exactly background free, but it's still, if it's very, very, very low background, then you can still convince yourself with one example.
Right. Okay, so uh, take take two collaborations, for example, Atlas and CMS. So even if they're investigating the same question, it's quite well known that they hide their data from the other collaboration because they don't want, confirmation bias to peep in. The thing is that what I want to ask you is that if there are people who are friends of each other working in different collaborations, or if they are married, or if they are spouses, girlfriends and boyfriends, do you really think that they don't tell each other what's happening in the other collaboration? Because
You
I've heard
know,
stories. I mean, I heard a story that there was this new particle that the CMS thought that they
mhm.
have seen, and that some people who are married to the other people who in the other collaboration they told those people about this possible new particle, and then when they saw their data, they also thought that, oh, probably we have a new particle, but then the CMS thought that, oh, no, we don't have a new particle, and then
Mhm.
Atlas thought, yeah, and there's no other particle because they were just trying to look for it. So they thought that,
Yeah.
okay, they have a new particle. So does
Mhm.
that happen often?
Well, I'm sure Atlas and CMS would like to everyone to believe that we always follow official policy, but science is people, and people are curious. And I remember when we were on the edge of declaring that we had discovered the Higgs at 125, and there had been bumps earlier. There was the paper about 115 at LEP, and there was the weird bump at 135 we saw, and so people were a little jaded. So I'll admit that I called up a friend of mine on CMS and said, do you have a bump and where is it? And when he said, yes, we do, 125, that was the first moment I really believed that we were seeing the Higgs. Till then, I was like, it's just another wiggle. So yes, people do talk to each other. And I don't know how other people's marriages work. I'm not married to a particle physicist, so I'm not tempted in that way. But I imagine that there are some interesting marital conversations. I mean, imagine sitting over breakfast with your spouse and your collaboration is about to scoop your spouse. You're not going to say anything? Like, really? I can't imagine doing that.
Right. Okay. So since I work in theory, so I don't have any exposure to this particular experience. But how is it like to work in very big collaborations like Atlas and CMS? I mean, For example, if there is a big discovery like the Higgs boson or some other discovery like G minus 2 discovery in the Fermi lab, um, how do experimental physicists feel like having, you know, about sharing the credit? Because there is no single experimental physicist who is ever going to be responsible for these big discoveries. So how do you live with that? I mean, it's very alien to me. It's very alien to me, to be honest. But I do know that you people live with that reality.
Yeah.
So how do you cope with that?
Look, there's wonderful things about it and there are terrible things about it, just like every other human endeavor. So let's start with the positives, okay? Because I work in a massive experiment, I can do things I could never do myself. I could never write a grant to explore, the 13 TeV energy scale. I could never build this massive detector myself and operate it. I could never do this kind of physics small scale on my own. So it gives us the opportunity to do kinds of physics we couldn't otherwise do. That's wonderful. The other thing, and something I think is not understood widely enough, is that it allows for specialization. It allows for all kinds of different kinds of experimental physicists. Like Atlas needs all kinds of people. We need people who really enjoy climbing around the detector and getting greasy with a wrench, and they just care about making that thing work. And to them, that's the crucial bit of experimental physics. And we need people who run the trigger and operation system, like actually gather the data and record it and get it on tape and make it all make sense. And for them, that's the most important piece. And we need people who nerd out about the statistics and think about what is this background and how do we do this kind of test and what about the look elsewhere effect? And how can we use machine learning? We need all those different kinds of people. And, sometimes you hear criticism like, oh, you're an experimental physicist, but you really just, work on the computer analyzing n tuples. But to me, it's a sign of progress in the field that we have specialists. Like I'm not going to go home and plow my own field and do surgery on my own appendix. I think it's a sign of progress in society that we have specialists who are good at that and get to spend their whole day just doing that. So, in the same way, experimental physics allows this specialization because we all work together. I don't have to be an expert on climbing around the detector in order to get to nerd out about the statistics. And the guy who wants to climb around the detector gets to do that. So, that's all the positives. On the flip side, you work with a big bunch of people and they're people. So there are jerks and there are loudmouths and there's a lot of politics. Who gets the credit for something when you work in a big team depends on who has managed to navigate themselves to the center of the effort and to be listened to. And that depends in equal parts on charisma and volume and aggressiveness, not just intelligence and clarity and brilliance, right? And it requires those things as well. So, leadership in experimental collaborations is just like leadership in any other human endeavor. The people who are in charge are the people who manage to get themselves to be in charge, which requires an interesting combination of traits, right? They have to think that's fun and exciting and important. Um, and, there's also a lot of, groupthink. Like a lot of people work on the kind of thing that everybody says they should work on. I'm actually quite concerned about how little training we give particle physics experimental graduate students in innovation, in creativity. The pipeline for being a graduate student in experimental particle physics is often like, we've been doing this analysis for 15 years. You're going to come and do this piece of it. You're going to improve it in this way we tell you. You're going to make that work. And it's work, and they work hard, and they produce something useful. But have they learned to be an independent researcher? Have they learned to come up with new ideas? Have they learned the difficulty of staring at the abyss of a problem that seems unsolvable and waiting for inspiration? To me, these are the crucial elements of being a physicist, a scientist. And I'm not sure we're always training people to do that. That's one reason why in my group I tend to step away from the areas that are the most hot topics because the politics to physics ratio tends to be much better if you take one step away. And so much physics at the Large Hadron Collider is undermanned. There's not enough person power to do a lot of really interesting physics because there's too many people trying to make this measurement of the Higgs whatever that everybody thinks is the most important thing. So, there's a lot of good and a lot of bad in experimental physics, just like in every other human endeavor. and it's personal. You got to see if it fits you or not. And a lot of people, they go to CERN and they fall in love with the environment. It's so exciting. It's like being at summer camp and you're working on a big project together. And other people, it drives them bonkers. And they're like, I can't believe I can't do anything without 16 people approving it, and arguing about commas and publishing a paper takes 4 years. It's insane. But just like everything else, you have to see, does it speak to you? Is it for you or not? And I love it. I think it's a lot of fun. I can't imagine doing anything else.
Right. I mean, the things that you mentioned that the people who are in a leadership position in experimental physics are not always the most brilliant people. I mean, they also have other traits like they have charisma and things. I mean, that's also true for theoretical physics to some extent.
Yeah.
So I can understand that because I think that that's a human thing. It's not
Mhm.
experimental or theoretical thing. But one thing that you mentioned is that we are not training graduate students in experimental physics to be independent researchers. Do you think that in this day and age, you can be an independent experimental physicist, right?
Yeah, it's a good question. It's hard to imagine doing that at the Large Hadron Collider, but
Mm.
there's somebody who proposes new colliders and new experiments and rises to be the loudest or clearest or most compelling voice in those conversations. And that takes creativity, that takes innovation, it takes breaking new ground and saying, hey, I think this is the right direction for the field, not just following the instructions that are on a wiki page that say, here's the plan for the next 10 years. Somebody's going to make that plan. We need leaders, not just followers. And so it's possible, yeah, absolutely, to be a leader, to break ground in experimental physics, but we need to train people to do that. We need to show them that it's possible. We need to show them that it's essential that they learn how to think for themselves. Um, and yeah, I'm not sure that always happens. When I'm
Mhm.
looking for postdocs, for example, and I'm filtering through graduate students, I see a lot of graduate students whose PhDs, contribute nothing new to human knowledge, except I've updated something that was done before with more data. So in that sense, it's new because you're using more data, answering more questions, but there's nothing new but the technique or the strategy. And I feel like that's a shame. It's a missed opportunity. I want my students to look back at their time at their PhD and think, wow, that was cool. I tried something really hard that nobody had done before and I made it work. I want them to be proud of it 30 years later. Um,
I mean,
and
I will admit that. Yeah, please go on.
No, no, and I was just going to say, and that's not easy to do always at Atlas.
Sure. I mean, I will admit that even in theoretical physics, it's a bit hard to, work on something that, people are not working on around you.
Hmm.
So yeah, so
Hmm.
being okay, I would admit that being an independent theoretical physicist is a bit easier than experimental physicist, but even that is not easy. It may be easier, but it's not easy because you may not get jobs if you work on something which is not mainstream, which is something which is totally disconnected from what other people are doing. So I think this problem is to some extent also exists in theoretical physics as well, but I can imagine that in experimental physics it may be a more dire problem.
Hmm.
Um,
Well, let me ask you about that because you touched on something which is sort of in the zeitgeist. The fact that theoretical physics follows, trends makes it seem too trivial. But, Sally works on this problem. You read her paper, you think that's interesting, you build on it, or you have an idea related to it.
yeah.
There's, I don't know about groupthink, but there is definitely momentum in theoretical physics where some things are explored deeply and other things are ignored. And for people outside theoretical physics, they have their great idea about how Einstein was wrong. Nobody wants to listen to them. It feels like there are some things that are discussed and other things are not allowed to be discussed or not given attention or whatever. So, how do you, as a young theoretical physicist, chart your trajectory where you want to work on something that's close enough to what people are doing that everybody's going to want to read your paper, but far enough away that they think, oh, this is new. This is your own thing. This isn't just like, an update on Sally's idea or something.
Yeah, but I think the thing that you're talking about, that there are some ideas that are not given attention, I think most of them are not given attention for good reasons, because they're
Mm.
not good ideas, to be honest. Uh, and the thing is that I'm also not a, big fan of chasing, or, you know, I don't think that you should always chase originality. Because the thing is that if everyone has its own theory, that's going to create a big mess. And I think, oh, okay, so I'm a young physicist, but I think one of the lessons that I have learned is that if you want to do good work, you should be comfortable with working on ideas that other people developed. So that should be fine. Um, but when I'm saying what I'm saying is that when I said that if you're working on something that other people are not working on, I meant that there are some problems that I want to work on, which are in the zeitgeist of what I'm working on right now. But those
Mhm.
problems will take a lot of time, and I don't think that if I can do that in my PhD or in my
Right,
postdoc,
right.
because they may take years to solve.
Hmm.
So the thing is that if I'm not working on those, and I don't think that anyone is working on those things because the problem is just too hard,
Give me an
right?
example. What's a big juicy problem that's too hard to
I
solve
mean,
in
so
5 years?
confinement is something that
Mhm.
I mean, nobody can solve it. So, yeah, I know, but the thing is that I want to try at least with some other people. But I don't know how many people are trying to solve confinement right now,
Mhm.
using ideas from holography and string theory and things like that. I'm sure people have tried, and it may happen that I may discover that okay, yeah, you cannot do it easily. But I at least want to give it a go. But I don't think that I can give it a go when I'm in my PhD or in my postdoc because my time is limited. So that's what I mean when I say that there are some problems that I want to work on, but you cannot work on those problems until you have a permanent job or you have a more powerful position. So I mean the thing. Okay, so loop quantum gravity is something that I may work on, or I at least want to give it a shot. I mean I have given it a shot to some extent, but I don't think that I can do it until I have a permanent position, right? Because it will take some time to learn it, and it may happen that I may discover that okay, what I was trying to do is a dead end, but that will just eat up my time of my postdoc or my PhD. So yeah, so these are two examples. There may be other examples. I have a list actually of a project list that I
Awesome.
keep. Oh yeah, I have a list, but there are some projects in that particular list that I will not attempt until I have a if I get a permanent position. So let's see. Okay,
Yeah. Well,
so
I think it's not widely enough understood that like physics and science, it's a human endeavor. And so it's driven by people like you with their lists, right? You have a list of things you're excited about. I have questions I want answers to. It's all just a bunch of people asking questions. I think a lot of folks on the outside of physics who are interested in science, but not participating in it directly or professionally, think that there's some like central institution churning out knowledge, but it's just a bunch of people being curious and asking questions and deciding like today, am I going to work on this or that or the other thing, or am I just going to drink coffee and think?
sure. So, as you mentioned before, you were also involved in the collaboration that discovered the Higgs boson, right?
Mhm.
So, were you anticipating as big of a media coverage of this discovery as it got? Were you anticipating that big of a media coverage?
That's a great question. I was definitely not prepared for the reception of it. I mean, I'd been around 20 years earlier when the top quark was discovered. I was very, very new to the field. And I saw that got some attention, but the Higgs discovery was much more massive in the sort of cultural impact than the top quark discovery. And maybe that's because CERN did a better job of the PR or just where we were in the world. Um, I happen to have made a video about the Higgs boson with my friend and collaborator Jorge Cham. I wrote him years before and said, "Hey, let's do some videos." And we did these videos, and we did one about the Higgs boson just before it was discovered. So it was like came out just in time so that when the Higgs was discovered, it got a lot of attention and millions of views, and it was um, a point of pride for me in my career is when they gave Higgs and et cetera the Nobel Prize, the Nobel Committee cited, read these links for further reading, and they cited our video. Our cartoon video of the Higgs boson. I mean, I'm never going to win a Nobel Prize personally. That's as close as I'm going to come, but it was cited by the Nobel Committee. That makes me proud.
Yeah.
So I was not prepared for how much coverage and how much excitement and how much enthusiasm there still is. I mean, I run a podcast also, and I continuously get questions about the Higgs boson. How does it work? Matt Strassler just came out last year with an excellent book explaining how the Higgs works, debunking a lot of the popular science molasses explanations. And it's fantastic, and it got a lot of attention. And so there's just this amazing continuing interest in the Higgs boson in the very popular audience.
Do you think that it got a lot of attention because people started calling it the God particle?
Yeah, it certainly could be. Leon Letterman's editors or whoever came up with that title could be responsible for it. And, unlike the top quark, it was a major discovery that was different from anything before, right? We'd never seen a scalar particle. It had been a long time since we've seen a new particle. The LHC made this big bet, and people argue about how many, promises the LHC made, but it really was sort of um, a lot on the line for the LHC, so it was very dramatic that we did see it. Personally, I was kind of rooting against it. I was really hoping before we saw the Higgs that we wouldn't see the Higgs and that we would see something else, something weird and crazy that made everybody go, "What? That doesn't make any sense."
Like
Because
supersymmetry?
I don't know, something even weirder than supersymmetry,
Okay.
something that wasn't anticipated, something that makes us just like go back to the drawing board and think about a new way to do electroweak symmetry breaking and rethink everything we know about physics. I mean, those are the moments you want to be around for, like the scientific revolutions, when you have some new piece of the puzzle and you're like, hold on a second. Who ordered that and what does it tell us about the universe? Discovering the Higgs and then nothing else is just sort of like it's a bit of a sad trombone, like, okay, yeah, the most vanilla explanation we have is the right one, and we learn nothing else. Like, okay, and it's an experimental triumph and it's technological wizardry, and everybody who is deeply involved deserves the credit they get for it. But it's not the outcome I wanted personally for the universe.
Right. At at that time, were people asking you that will Large Hadron Collider create a black hole that will swallow the
Oh
Earth?
man, absolutely all the time. I get that question so much. I still get questions about that. These days, actually, the question is more often, will the Large Hadron Collider collapse the Higgs field? Right? Um, People are worried about that.
What does that
Um,
even mean? It's not a wave function.
no, but what if the Higgs field relaxes? What if it's
Oh,
unstable
okay.
and it no longer stays at high potential energy and relaxes down to lower
Right.
potential energy, and the Vev goes to zero and electrons lose their mass and all atoms explode at the speed of light. Dot dot dot. Bad. Um,
That's strange. That's strange. Okay.
yeah,
So,
but I love the interest. I love that there's so much interest in particle physics and the Large Hadron Collider by lots of folks out there in the world. I think it's wonderful.
I mean, not all of the interest is actually good because a lot of people
Hmm.
think that, CERN is like a place where Satanists live,
That's
and
right.
worship the devil.
That's where
And
we talk to the devil. Where else do we get our instructions? That's how we open the portal of hell. I don't know how else
oh
to
yeah,
do it.
yeah. So all the interest is not good actually. Some of the interest is like that. Okay, so uh, i- in the discoveries regarding particle physics,
Hmm.
there is this benchmark that people have come up with, which is called the 5 sigma benchmark, which
Hmm.
means that the discovery that you are doing, the chance of that thing happening by chance is something like 1 in a million, something like that. So do you know how people uh, you know ended up on that particular benchmark, and do you know if this benchmark is universal? For example, people working on gravitational physics or people working on other fields, for example, things related to cosmological observations, do they also use 5 sigma, or can they settle for less?
Yeah, that's a great question and really interesting history. I mean, you mentioned the reason we need to quote this is that we want to convince ourselves that we're seeing something that's not just a fluctuation. And so typically we measure the probability of this being a background fluctuation, like some alternative hypothesis. What if that particle didn't exist? What are the chances of seeing this data under that hypothesis? And you want that probability to be very small so that you don't claim a discovery that isn't real. And I think that a lot of this is just cultural. Like, number one, CERN and particle physics in general is very, very conservative. They are desperate to avoid making a claim of a discovery and then having it turn out to not be true. And you can imagine, I'm not advocating for this, but you can imagine a different scenario where you're like, okay, look, we're going to report every 2 sigma fluctuation, and some of them, are going to not be true. In fact, 5% of them, if we're frequentists, are going to just be fluctuations, and you're just going to have to live with that. But I think that particle physics has decided that the statistical fluency of the general public isn't deep enough to appreciate that. That when we say, "Hey, here's a bunch of discoveries, 5% of them are wrong," that people are going to understand that, and so they've decided to be very, very conservative. And the history of the 5 sigma has to do also with our inability to correctly calculate an important statistical effect called the look elsewhere effect, which relates to p hacking, right? If your threshold is whatever it is, 1 in 1,000, 1 in 10,000, an easy way around that is just to do a large number of experiments, right? If I expect a fluctuation once in 10,000 experiments, and I do 10,000 experiments, then I'm going to see that fluctuation once. I mean, on average, right? And so if I report only that one with a fluctuation, it can look like I've seen something dramatic. And that extends to 2 sigma, 3 sigma, 4 sigma. And so we publish a lot of papers on Atlas, and each one we treat independently statistically. We say, this one has a 2 sigma fluctuation, this one has a 4 sigma fluctuation. But the denominator really is much larger than we're accounting for in each individual paper because we're not accounting for the fact that, okay, we're reporting 4 sigma today, but we reported 3 sigma last week and 2 sigma, a bunch of times. And so there's lots more possible experiments that we would have accepted as real signal if they had shown something that we're not accounting for. So 5 sigma is like a conservative way of saying, all right, let's just ratchet this requirement up really far so that it becomes almost impossible to hack it, even with p hacking, even if you do a bunch of experiments. It's not a very robust way to deal with the look elsewhere effect. What you should do is say, all right, here's all the different things we studied. And so we can actually measure the background probability in any of the experiments we did, not just in this one narrow category. But that's very difficult to do. I'll give you a personal example. One of the most fun moments for me in the Large Hadron Collider was when a student came to me with a histogram. They were looking at some data, and it was same sign muons. And they were looking at it because they were just trying to study the background shape. And, in same sign muons, you don't expect to see a peak. There's no resonance that decays to 2 positively charged muons. But he showed me this peak at 105 GeV in same sign muons. And he was like, did I do something wrong? What is this? And for a moment, I thought, oh my gosh, is this the moment of discovery right here? Am I looking at a plot which like is going to be in textbooks and people are going to write stories about, what we had for lunch today? Is this all of a sudden super duper interesting? And so then I said to him, well, that looks really compelling. How many histograms have you looked at before you picked this one to show me? And he's like, oh, I don't know, thousands. So, if you look at enough histograms, you're always going to find one with a fluctuation. You don't know. I don't know. Without knowing how many histograms he looked at, I can't tell how significant this is. Anyway, we analyzed that histogram for 6 months, trying to figure out whether there was something weird going on. Then we looked in the rest of the data and we saw an exactly opposite fluctuation downwards, so that the full data set had no peak at 105 GeV. So I don't know. 5 sigma has no special meaning. It's just like historically ratcheting up this threshold to avoid being bitten by the look elsewhere effect. And I think that it's become pretty pervasive, but I'm not an expert in like statistics and cosmology.
Right. But the thing is that if you want to achieve 5 sigma, it means that you will have to run the experiment for a longer time, right?
You have to run the experiment for a longer time. I have to think about
Because you
that.
need
You
because you
need a
need to collect more data, right?
Well, you need to collect more data depending on the size of your background. If you really have very, very little background, you convince yourself, if you have no background, then one event is above 5 sigma, where nothing has no background. But if your background is small enough, then you could convince yourself that a small number of events could be significant enough if you understand your background well enough. Typically we don't, and you need data to understand the background. So you're right, we need large amounts of data to establish our understanding of the background, and then establish five sigma. Yes.
Right. So, does it ever happen that there are some PhD students who are working on a project and they say that, I mean, we need to complete our PhD. So if we wait for Five Sigma, I think it will be very late. So can we just release can you release the results right now? So does it ever happen? I'm pretty sure it would happen sometime.
It
Does it
does for sure. But you can write papers before you have five sigma. You just have to use different words. Like four sigma is observation and three sigma is evidence. And I remember when we were finding single top production. So we'd already found the top quark. This is the Tevatron in the late 90s. We'd found the top quark and we were interested. Was it really the top quark we thought, or was it something else? And one way to test that was to look for production of a single top instead of top pairs. This is much harder because the backgrounds are larger and the cross section is for the signal is smaller. So there's a race between CDF and D0 to who could get the first five sigma. But along the way, there was a race to get who could get the first four sigma, who can get the first three sigma. And I remember one moment when CDF had 4.01 sigma and D0 had 3.97 sigma, and CDF was celebrating that our paper could say observation and their paper had to say evidence. Like it was a meaningful difference. Obviously it wasn't. But you can publish papers along the way before it gets to five sigma.
right? Okay. I mean, does it ever happen that there are two collaborations working on a project, and one collaboration wants to publish, but the other one says, no, no, not right now?
That's a good question. I don't know what the protocols would be there. I think that one collaboration can just publish on their own as long as they let the other one know. Usually at these large labs, there's a rule that you can't like have a press conference without giving the other collaboration a certain number of days notice saying, by the way, we're going public. If you're about ready to go, we should do it together. And collaboration two can't veto collaboration one, but they can join them in the press conference if they're ready.
Okay, I see. I see. So you also use machine learning for, understanding particle collision. So what kind of, tasks does machine learning do in your research?
All sorts of stuff. I mean, the classical way we use machine learning is to help us avoid simplifying, simplification with heuristics. Like we have huge data sets with high dimensionality, too high dimensionality for us to model or understand or reliably do statistics on. And so historically, what we've done is boil that down to smaller number of quantities that we can understand. And that's effective and it's worked for years, but it loses information. And so, historically or classically, neural networks and machine learning is very powerful at stepping back up to higher dimension problems and pulling out more information than you can get from like human designed heuristics. So, if you can attack the problem in higher dimensionality, you avoid losing that information. And that's awesome and that's wonderful. But machine learning is much more than just that. Machine learning, for example, is allowing us to look for non-helical particles in the tracker in a way that we couldn't ever before. Tracking is a very hard problem. You have to find a set of hits in the tracker, connect them into a line, and say, I think this is the path of a particle. And that other set of hits over there, that's not. That's just a bunch of random noise that looks kind of like a particle. And to do that, it's a huge combinatorial problem. Like imagine thousands and millions of hits. Now consider every 8 or 10 or 40 hit subset of that. Like it's just too big a problem to solve brute force. So we have heuristics. And those heuristics say, let's only look for particles that go from the inside out and start from the vertex and move in a helix, because otherwise the problem historically has been too hard to solve. And so that means baking in to our tracking algorithms the assumption that it's a helix. And recently, however, machine learning has been able to solve this tracking problem in a totally different way. We train a neural network to identify patterns of hits that come from a track, and that and we don't build into the machine learning the assumption that it's a helix. It's in the training set. We train it with a bunch of examples of helices, But we recently used the same pipeline and gave it a different training set, non-helical tracks, to see, hey, can it learn to find non-helical tracks if you give it a bunch of examples? And the answer was yes. And it's actually quite powerful. And we just put out a paper on this where we demonstrated that if you train a tracking algorithm to look for quirks, it can find them. It can find these spectacular tracks in the data, in the simulated data. We haven't yet unleashed it on real data. But that's an example of how machine learning lets us do things that were long thought to be impossible and now are possible. So it's exciting because, it opens doors that have long been closed.
So, when you talk about neural networks and deep learning, there are different architectures that people use. So, what kind of architectures are used in your work, like feed forward or RNNs or CNNs or things like that?
All sorts of different stuff depending on the problem. Often we'll start with simply full connected feed forward networks. But sometimes we do things like anomaly detection, where you want to take a problem and then you map it to some latent space. Can I transform this problem from this space to another space and then transform it back and see how well does it transform? That can tell you a lot about something. Concretely, if you want to take, for example, a set of hits on a track and then map it to a latent space where instead of having physical space of the hits, your latent space is now the parameters of a helix. Well, if you train a neural network to map helices from hits to parameters and then parameters back to hits, it can do that. Now, feed in something that isn't a helix, it's going to fail to do that because it can't be mapped into that latent space. And so you can use that as a way to detect non-helical tracks, for example. So we have all sorts of different kind of architectures. And in my group, I actually have some students who are theoretical physicists, and they're using machine learning as a way to explore theoretical physics problems.
Right. So you also do some phenomenology with you know theoretical
Mhm.
physicists who are uh, building models to test in the experiments. So I want to talk a bit about that, but for the people who don't know what it is, can you define what is phenomenology?
Yeah, sure. So I'm not by training a theorist or a phenomenologist. I'm an experimentalist, but always been interested in the sort of questions that underlie the whole field, which of course are theoretical questions. And I like theorists. I like talking to them. I like working with them. I like excuses to collaborate. I also, like excuses to do things outside of the collaboration. We have 6,000 authors arguing about commas. And so it's fun to work on projects outside the collaboration. So I have a whole series of papers that you would call phenomenology, where essentially theorist comes up with a particle, a new hypothetical particle, the squiggly and we explore in that paper what is the LHC's power to discover the squiggly? What would it look like in our detector? What are the backgrounds to it? How could you possibly reconstruct it? And the answer to the science question at the end is, the LHC would need this much data to have a significant discovery of the squiggly. So it's an exploration of the power of the LHC data set to see this new kind of particle. And this is a particularly fun kind of project because it's outside the experiment and it's very well suited to undergrads. Undergrads can do this kind of work, sort of a simplified version of the experimental analysis pipeline, and they can use MadGraph and Pythia and Delphi's and this kind of stuff, get a taste for experimental physics without having to go fully into the Atlas software environment.
Do you think that the collaborations between theorists and experimentalists have evolved over time, as compared to 1980s? Now they are much less frequent, or do you think that that's not the case? It's just a myth.
Yeah, that's a great question. I mean, I'm not young, but I'm not old enough to have been around in the 80s doing particle physics. My experience is that most theorists don't talk to experimentalists, and most experimentalists don't talk to theorists. And I've also had the experience of going to the experimental leadership and saying, "Hey, I want to look for this new weird thing," and having them say to me, "Well, there's no theory paper on that idea." So I know, but we have the idea. They're like, "Well, there's no theory paper on it, so you can't do it." So then we go and write the theory paper with the theorists, and then I can come back and say, "Okay, now we have a theory paper. Can we do this?" And they say, "Okay, yes." And to me, that's like missing the point. The point of experimental physics is not just let's check the ideas of the theorists and only look for theory approved concepts. That's stuck in a mindset where theory is leading the field, and it's fine for theory to sometimes lead, but experiment should also sometimes lead. We're explorers. We're the ones asking the universe questions. We should be out there looking for new stuff that's not anticipated, that makes everybody go, "What? I couldn't imagine that would possibly be the answer to the question." We shouldn't restrict ourselves to only look for things that have like a theory approved stamp. So I like talking to theorists. I can't speak more broadly to, whether things have changed since the 80s, but I think we should have more connections between theorists and experimentalists because it's fun. you know, it's a good time.
When you say that, less theorists talk to experimentalists, do you mean people in formal theory or people who are doing phenomenology?
Definitely people in formal theory. But also I think a lot of model builders. I've worked with a lot of model builders on papers, and it's often the case that they've never worked in detail with an experimentalist before. And there's this feeling that the communities are just separate, and they are different. You come up into the community from a different path, right? You're a theorist or you're an experimentalist. You take this set of classes, that set of classes, this kind of postdoc, that kind of postdoc. And so they come from different communities. They aren't used to always working with each other. So yeah, I'm a lot of people's first experimentalist to have collaborated with. Um,
I see. I see. So, do you think that does phenomenology ever become too optimistic in discovering new phenomena? And what have we learned from those cases?
Too optimistic. Um, I don't know. I think it serves a useful purpose. It explores, what's possible to see and what's well motivated, and it takes the first steps in figuring out how you could do it experimentally. I'll be honest that I was a little surprised when I discovered that this was a whole discipline, that between theory and experiment, you could write these papers that were like, well, we didn't do the experiment, but we sort of sketched out how you might. I'm pleased that it's possible because it gives an avenue for undergrads to contribute and to get to write papers and learn about the scientific method. Um, but I don't think I knew the phenomenology was sort of a thing separate from theory and experiment when I was like sort of a young physicist growing up.
So,
Surprised me.
do you think that if we want to bridge the gap between theorists and experimentalists, we can do some or start some, workshop where we have both theorists and experimentalists? I don't know how would that work, but do you think that this is, an idea that some people can work on, or do you think that this is not practical?
I think we should definitely figure out how to do it. I'm not sure how to do it. The problem is it has to be sort of organic because people have to have fun working on it. So you have to, the way it's going to succeed is people on both sides of the aisle have to find fun projects they want to work on together. And sometimes you can make that happen by arranging a workshop, but sometimes that feels, like you're trying too hard and it doesn't really happen. It's just sort of like throwing a party. Sometimes you throw a party and it's a lot of fun and people come and make connections and, tell stories about it for years. And other times you throw a party and it's just a bunch of awkward conversation and nobody really, makes any connections. Science is just people, right? And it's like arranging dates or parties or friendships. So yeah, for that to happen, they have to interact because then you have to discover places you can collaborate. And I think machine learning is a great way for that to happen because there's a whole vibrant machine learning particle physics community that used to be dominated kind of by experimentalists, but now a lot of theorists contribute because they see the value in developing these machine learning techniques that allow us to do new things in theory, especially like in QCD, for example, where things are already so complicated that you couldn't do before. So guys like Jesse Thaler, like definitely a theorist, but huge contributions to machine learning and collaborating extensively with experimentalists like me or with Ben Nachman or other folks on the experimental side.
Yeah, that's actually a good point. I mean, machine learning can be, something that, theorists and experimentalists have in common. So yeah, that can be a factor that can bridge the gap. Are there any so you said that you have worked on some phenomenological models where there was no theory paper, but then you wrote the theory paper, and then then you were allowed to test the consequences. So, do you know any lesser known phenomenological models that you think deserve more attention?
What a great question. I don't. I wish I did. I wish I was capable of coming up with new phenomenological models. Usually, that's the role of the theorist in my collaborations. The conversations start with, "Hey, do you have any new ideas for a theoretical model that we could explore in a phenomenology paper with some undergrads?" And then they come back to me with some options. That's how the Quarks project started. Um, I wrote a paper last year about single heavy top partners that started that way, working with Max Feig here at UC Irvine. He had an idea for how this hadn't been explored before. Um, but no, I'm not usually the source of those ideas. I wish I
Right.
was.
I understand that. I mean, I'm not saying that you have to come up with the idea, but
Uh,
in your collaboration with phenomenologists, have you come across some idea, some phenomenological model
mm,
that is not very well known, but you think should be more well known because you think that it has some potential to be true?
mm. I think that there are a lot of fascinating phenomenological models of dark matter that should be more deeply explored. To
Hmm.
me, it feels like there's a lot of potential there, and there's a few avenues people have explored, and a lot of folks like Tim Tate here doing really new creative stuff. But it feels to me like a very vast open territory, and I wonder sometimes if we are limited by our mathematical intuition. Theorists go off into this space of all possible models and try to build something which is going to work and be intuitive and elegant, and also conform with observations, but they're not, they're relying on inspiration, not exhaustive systematic search. And so I actually think that machine learning can really help us in exploring the space of these models to find new areas of phenomenology that we hadn't considered before, because they weren't attractive to theorists, or they didn't come from some moment of inspiration or conversation or building on something else somebody had done. I think it might be time for more systematic exploration of these ideas. I'm working on a project like that with my postdoc, Issac, who's a real whiz at machine learning and is also interested in theoretical physics.
See, I see. So, it may be a very vague question, but just to get your some of your priorities here. So, if you could set the agenda for phenomenological research for the next 5 years, what would be your priorities? I mean, the answer doesn't need to be very precise, but if you can give any vague answer to this question, what would be your
Wow.
priorities
Priorities for phenomenological research.
for the
Um,
5 years, the next 5 years?
yeah. I think it's important to understand the potential power of new facilities. People talk about the muon collider or these other options we have. I think it's important to know what physics could we do with them. What power do they have to discover things that are unexpected? These are hard questions. When you talk about things that are unexpected, you're like, well, what do you mean? And you have to enumerate them or somehow define them, and then they're no longer unexpected. So I think that's a really important problem, making sure that the directions we're going in the future give us opportunities to discover things that we don't anticipate now. I don't know how to solve that problem, but I think that's an important part of that conversation. And I think without that, we risk being too concrete about what we might do with those colliders, and then being accused of not delivering. I don't think, for example, to build a muon collider, we have to know this will discover A, B, C, and make claims about it. I think it's enough to say, hey, this muon collider is an exploration into the unknown, and we don't know what's there, and it could be nothing, and it could be something awesome. Let's just go see, because to me, that's the excitement of experimental physics is let's go explore. Um, but we've sort of gotten into this pattern of promising discoveries for new colliders that I think is a mistake. I don't think we need to do it. I don't think we can do it. I don't think it's valuable. I don't think it's something we can promise. And so I think it would be great if phenomenology could help us sort of sketch out the possible space of things we could explore with these new colliders somehow without enumerating and promising those discoveries. I don't know how to do that though. It's too big a problem for me to work on, as you say.
I mean, you said that we don't need to do it, well, by which you mean that we don't need to, promise discoveries before the collider is made, right? Are you sure about that? Because the thing is that the people who are going to give the money, they're not scientists, and
Yeah.
it's hard to sell them the idea if you don't promise.
Is
So do you
it? I
think?
mean, we sell them the idea of landing a rover on Mars without promising that there's going to be life
Yes.
there. It costs the
Okay,
same, right?
that's
We
true.
there's lots of places in science where it's exploration and it's sold as exploration because we just want to know what's there, and probably it's nothing, but it's worth going to check. And I just think we're selling it wrong. I think we should be selling colliders the way they sell rovers, not by promising discoveries.
I mean, if you look at what happened to superconducting super collider, do you think after what happened to that collider, can you really trust the politicians? you know, because the thing is that if you don't promise anything, it's very hard to get money for these kind of big projects. So I mean,
Yeah.
it's like that in America. I don't know what's it like in Europe. So do you think that we don't need to promise anything, or do we need to dial down on the promises, but still we need to have some promises? Otherwise, the money is very hard to get.
I'm no expert in politics, but I think that we should be honest with the public and we should connect with their sincere curiosity about how the universe works. They want to know, they're curious, they understand exploration and curiosity. And I think the more we connect with the sincere curiosity of the broad public, the more we're likely to get broad support, which I hope translates to support from politicians and therefore money. Because the whole reason we get to do this is because people are curious. If everybody around the US was like, you know what, physics, what a waste of time,
Well,
and
I
they just
mean,
turned off the spigot, then we couldn't do this anymore.
a lot of
And
people are like that actually.
exactly.
Yeah.
And I think that there's a real danger of that. And we need to remind people why we're doing this. Not because, hey, we're going to invent a new transistor. We're doing it because we're curious about how the universe works. And oh, yes, that does come with transformational economic change in your country and research that leads to impacts that change the way we live our lives and the iPhone and all that kind of stuff. But we can't promise that in a sort of a quarterly report and say, we know it's going to happen. It always has, and research is the best investment anybody's ever made in anything, basic research, that is. But I think that we need to connect honestly with people's motivations for why we're doing this. We're doing it for the same reason we want them to be excited about why we're doing it. So I think selling it based on, technological spin-offs and promised discoveries is the wrong way to go because it's a trap. And already it opens us up to criticism from folks like Sabina who say, oh, you sold the LHC on the promise of supersymmetry. I mean, I didn't promise anybody we were going to find supersymmetry. And so now people say, well, why should we build anything else? Your last one failed. So I think there's a real danger in making those promises.
Yeah, well, I mean, a lot of criticisms of Sabine are in bad faith, so I don't take them seriously. I mean, a lot, not all of them, but not a lot of them.
You may be right, but she has a large audience and they like
That's
to hear
true.
those and it affects them. It changes how they think.
I mean, I think it's sad that she has a large audience, but she has a large audience. We cannot do anything about that. But the thing is that uh, I don't know if somebody promised supersymmetry. If somebody did, I can tell that, yeah, that person shouldn't have done it, or those people shouldn't have done it. Those people should have said that, we expect to discover it, but we cannot promise anything, of course. So, yeah, I don't know if they promised it or not. But anyway, so, one story that always comes to my mind when I, talk about these kind of topics is from Steven Weinberg's book, Dreams of a Final Theory. And the story goes like this. So he was testifying in front of Congress, Congress or yeah, I think Senate, about, why do we need, superconducting supercollider. And one of the, senators said to him that we will give you all the money if if this particular collider helps the work of Stephen Hawking. Now, I think that's a very immature response. I mean, why? Because Stephen Hawking is famous. Is that the only reason? So, I mean, when I hear these kind of stories, I tend to get the idea that the people that we are dealing with here are, I mean, kind of very naive about science. So, we need to tell them at least something that we expect to discover. We don't need to promise anything, of course. But if we just go there and say that we are doing it for exploration, I rarely see any example of a big scientific project that was funded just because of exploration. I mean, some people say that we landed on the moon, but I think we were we were, America was in war. I think that was one of the driving factors why people supported going to the moon. And some people make the argument that the reason they started funding the superconducting supercollider was that they were, America was in Cold War, and as soon as Cold War ended, people stopped thinking that physicists are important. So, do you really think that any a big scientific, project has been funded just based on curiosity and exploration?
Yeah, well, I think the big space telescopes, James Webb Space Telescope, who knew what it was going to find? We just wanted to create new eyeballs to look deeper into the universe and see new things. The thing about telescopes is that they always do discover something because the universe is crazy and bonkers and filled with surprises. So that's, they have a wonderful track record. So I think astronomy and planetary science and these kind of things, I think they are motivated by curiosity and exploration. And you might be right that selling these things based off exploration will fail. You might be right, but I think it's honest. For me, it's the reason we do it, and I think we should be honest about why we do it, because then we can't be criticized for being disingenuous because we weren't. And I believe that people are curious, that they want to know, they want us to explore. And if we're serious about it and honest about it and communicate clearly about it, we can, enhance that curiosity in the general public, which is a good thing. And we can tell them more about how science works. And so I could be naive. I'm not a politician. I'm also not a leader in the experimental physics community, probably for a reason, because I'm not an expert in these kinds of things. But I feel like we should be honest with the public and sell to them for the reasons we're doing it, because there are a lot of people out there who want us to do it for that reason, I think.
Okay, so let's talk about something that is related to what we are talking about right now, which is communicating science to popular audience, and you have done that a lot. You made this series named Elinor Wonders Why with your
Mm-hmm.
friend Jorge Cham.
Mm-hmm.
So and it was nominated for Daytime Emmy. So making this kind of series can be very challenging. So what were the main challenges that come in your way when you were making this series?
Knowing at all how to make a television show. Like, we wrote a proposal for this thing and we had an idea for what might be a cute show. And I thought it'd be really fun to show curiosity in children and encourage it and show kids how to answer their own questions. And so we wrote this proposal. But as an academic, you write proposals and you submit them and you forget them and you give up on them because mostly they're not funded. So when PBS came back to us and they were like, "We love your idea. Make us an episode as an example, a pilot." I literally typed into Google like how to make TV show, because I had no idea how do you do it, like from nothing. So we had to learn everything from scratch, right? Jorge had never made a TV show either. So PBS was wonderful because they guided us in the process. They introduced us to animation studios and they told us how things usually work. So we had to learn, what's the production process like? How do you write a script for an 11-minute show? How do you hire a team of writers? How do you contract with an animation studio to create your show? What are the steps involved in like approving it? Um, and it was fascinating. I mean, one of the reasons I do science communication is that I'm always learning something. Like, how does this whole system work? How does a television show go from zero to on the air, the soup to nuts of it? Um, so yeah, it was a lot of fun. I didn't realize, for example, that when PBS picks your show and says we want you to make it, they don't pay for it. If you pitch a show to Netflix and you're like, "I have a great idea for a show. Here's the budget." They're like, "Cool." They write you a check for the whole budget. You go, you make the show. PBS is like, "Okay, here's your $20 million season one. We're gonna pitch in 8 million. Go off and find $12 million." to complete the budget. So you're like, I don't have $12 million. So that's a project, right? That's what the executive producers do. That's why you see them on the title screen getting credit near the top because they often find the money. But then you got to hire everybody. And it's this weird situation where you are, in principle, in charge. So you're making these decisions, but you're employing people who know a lot more than you do. So, for example, we hired musicians to create music for the show. I'm not a musician, Jorge's not a musician, but we're listening to what they create and giving our thoughts on it. And I'm like, how am I qualified? I'm a particle physicist. How am I qualified to know whether this horn sounds good, at this point in the show? It's just sort of like trusting your own artistic and creative instincts to produce something that you think might be good. It was a lot of fun, though. I learned a lot, and it's been a wonderful project.
Oh, right. So, but were there some other challenges? After the thing was made, were there some challenges in the distribution or something else?
A lot of challenges along the way. Something I didn't anticipate is the challenge of communicating science to 4-year-olds. You can communicate basically one idea. You have 11 minutes, you can communicate one idea, and you have to do it like 3 or 4 times because when 4-year-olds watch your show, they're not always paying attention. Sometimes they're picking their nose, sometimes they're staring out the window. And we tested our show on 4-year-olds. Like real life 4-year-olds came in to watch the show, and we stood behind a one-way mirror watching them watch our show. Like, hey, did they pay attention? Did they laugh? And it was so frustrating because I'm like, you missed the joke. You were picking your nose, and we made this great joke. We spent like a whole day on that joke, and you weren't even paying attention. So you have to be really careful not to put too much into the episode because really just one idea can be communicated to 4-year-olds in 11 minutes. So that was a real challenge, just like simplifying it that much, finding questions that could be suitable for the show. And then once the show launched, yeah, distribution, merchandising, spin-offs into books, all these things were new challenges. And the challenge there is that as the show continues, it needs to find ways to support itself. PBS will continue to support you, but their contribution decreases every season. So you need to find other sources of revenue, selling the music rights, getting sponsors, making plush toys, all sorts of ways. The shows that have lasted a long time on PBS, Sesame Street, Arthur, the way they do it is they find outside sources of revenue to continue to support the production of the show. It's a real challenge.
Do you also, I think you can also start your merchandise, right?
Yeah, we have a merchandising team, and so you can buy Elinor Wonders Why stuff at the dollar store and at Whole Foods and all sorts of stuff. Yeah, absolutely.
I do remember that when I saw Dora the Explorer for the first time, I used to think that why is this show so slow? But then I realized that this is slow because it's for kids. I mean, and for kids, you need to make it very, very slow.
Yeah,
Otherwise, if you put too much in, they will
yeah.
not understand what's going on. So, was there any particular idea that you found really challenging communicating to kids?
Oh man, there were so many ideas that we wanted to do shows about, but were too tricky. And one, for example, was color. I wanted to help kids understand like why are things green or why are things red? And I tried so many ways to tell a story, a fun 11-minute story where the kids think about color and understand something about light. And man, it's complicated. I have trouble sometimes explaining to adults like the thing you see is blue is not because it's absorbing blue light, but reflecting blue light. This is like mind blowing to adults. And so to 4-year-olds, I never successfully got an episode made about light and color. There's so many things. We made 80 episodes in the first season, which is a huge number, and we had to start from like 600 ideas for episodes because so many of them fail along the way. The pipeline is brutal. And you get notes from the animation team, you get notes from the director, you get notes from PBS, you get notes from education specialists. It has to pass through so many hurdles before it actually makes it onto the screen. But then it's wonderful when it finally does.
Right. I'm actually curious. What do education specialists do in this?
Well, we had two different categories. We had science consultants. So sometimes we'd be working on a topic where like So sure, I'm a scientist, but I'm not an expert on butterflies. I want to make sure that our episode on butterflies is like rock solid, accurate on butterfly science. So we'd reach out to a butterfly researcher and make sure, is our depiction of this correct? Is our description of this correct? So there's one side of the science consultants. The other side are education specialists who know how kids learn, how to teach them a concept, because there's a lot of research that goes into how to teach people. And physicists like to invent things themselves and think we're the best at everything, but there's a whole field out there about how kids learn. You know, how you scaffold an idea. Will kids understand this? If you explain this in two different ways, is that helpful or just confusing? And so we had a wonderful educational consultant who really helped us understand typical levels of knowledge of kids and what things might be confusing and how to portray it and how, especially to make the stuff on the screen work well with the words, in order for the kids to handle it. And there was another avenue to that, which I thought was really fascinating, which is speaking to the adults in the audience. Because, you're four, you're watching it, but probably there's an adult also watching with you, or they're making dinner while you're watching it. They're using it as like cheap babysitting, but they're hearing it. And I also wanted to speak to the adults because I read a bunch of papers that said that parents and preschool teachers often don't talk about science to their children because they're afraid their children will ask them a question they don't know the answer to. And to me, that's a huge missed opportunity. So in our show, the kids ask questions of the adults in the show, and the adults don't know the answers, but it's fine. They figure it out together. The adults always say, like, I don't know, let's figure it out. How would you figure it out? So I wanted to sort of, in a sly way, teach the adults in those kids' worlds how to talk to their kids about science. Make, hey, it's okay to not know the answer. Look, the dad on TV didn't know the answer. He's not embarrassed. So that was sort of a secondary goal of ours.
Right. And were there some concerns that some topics, although they seem, harmless, may be a bit problematic if you put them in a program for children? For example, can you say that when two, when two animals reproduce, can you say things like that, you know, in a show like this?
It's PBS, and PBS is very careful to not offend anybody. And
Mhm.
so, yeah, we had to walk around those kind of topics. We also had to walk around topics like, we had tried to have an episode about relationships between animals. Like how is a monkey related to a hippo, related to a giraffe? There's similarities and there are differences. Um, but they thought that was a little delicate because we're like comparing fur color, and that could have been an analogy for skin color, and they just didn't want to get into anything political.
Right.
They're trying to just focus on the science and not say anything which could be interpreted as a political statement. So yeah, and the audience is 4 years old, so
Mhm.
it's definitely sanitized. But there's a
Oh,
lot of science you still can cover. We talked about smell. We talked about, how does Velcro work, and how is it inspired by burrs in fur, and why is ketchup goopy? And there's a lot of really fun science to talk about with kids. It
right,
wasn't
right, right.
limiting.
Right. Okay. So you also, okay, and right now you have a podcast which is called Daniel and Kelly's Extraordinary Universe. But previously you had a podcast, Daniel and Jorge Explain the Universe. And so you have been having a podcast for a long time. So how did, having a podcast, okay, did it happen that having a podcast change your style of science communication?
Yeah, absolutely. Having a podcast really changed my style of science communication. It helped me connect with the audience out there because they're responsive. They write back comments to the podcast, they ask questions. It gives me a sense for what people want to know about, what they're into, what they like hearing about. It made me more comfortable being myself because I noticed that people responded positively to personal comments, not just science. There's all kinds of people out there. Some people want a short podcast that's just like science, 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 science. But a lot of people out there also just want to kind of get to know you and listen to you every week and sort of become your friend a little bit. And so if you talk about who you are as a person, it helps them know you. And so, I make comments on the podcast about like how I prefer dark chocolate and I don't think white chocolate is really chocolate. I mean, it's just silly. We make jokes. And I got a lot of emails, a lot of emails. People like, thank you, for standing up for dark chocolate. And I agree with you. And other people are like, how dare you? And, it's all in good fun, but,
Yeah.
it connects you with the audience in a fun way that you don't get if you write a book as much. I don't know. I find the podcast audience is more responsive in that way.
Right. I remember
How
that.
about you? Do you is having a podcast changed the way you think about science communication and what the general public know out there?
Well, so the thing is that the podcast that I'm doing, most of the audience for this podcast is, advanced undergrads or, beginning grad students, or sometimes even more senior people. Sometimes people from high school do watch this podcast. So one thing that I started to do is that if we use any jargon, then I put the explanation of the jargon in the podcast. So that's something that I started to do, and that actually made me realize that um, a lot of jargon can be explained using non-technical terms in one or two sentences. So sometimes I used to think that, well, I mean, if I have to explain jargon to people, it may take a long time. But when I actually tried to do it, I understood that you don't need to explain the jargon to the very fine last detail. If you just give them an idea of what you are talking about, it can be done in one or two sentences. So it's not that hard. So that's something that I learned from, having a podcast, and especially for the last 15 or 16 episodes, because before those episodes I didn't used to do it. So that's one thing that I learned from having a podcast. Apart from that, I mean, if you watch some of my earliest podcasts, I mean, they were not in English. I mean, I used to have speak my mother tongue. I was very awkward, and I didn't know how to hold a conversation. I mean, holding a conversation is an art. I mean, it's not very
Mhm.
easy to do. So
Mhm.
sometimes if you don't know how to hold a conversation, the guest has completed his or her answer, and you just don't know what to say. So that's very awkward. So yeah, so I have learned that how not to have those moments, and
Mhm.
how to keep a conversation going by coming up with good questions, or any more talking points, or expanding on things that the guest has said. So that's something that I have learned, and of course these kind of things also help you in your life outside the podcast, because that just
Yeah.
makes you a better person to have a conversation with. So that's something that the podcast has taught me. And the thing is that I would say that even before having the podcast, I was good at conversations. But if I talk to a person who is a big name in the field,
Mm.
yeah, then I would get starstruck, and I didn't know
Mm.
how to talk to that person. So having a podcast has kind of diminished my fear in that particular category. So
Mm.
if I now talk to a person who is a big name in the field, and someone who I have looked up to for a long time, I would not mumble. I would not stutter now, right? So that's something that the podcast has taught me. But it may happen that it will taught me it will teach me some other things in the future. But right now, these are some of the things that I can point to. So it's good to know. Okay, so one thing that I wanted to ask you is that okay. Before I go to my next question, I think we have mentioned the name of Jorge Cham many times. If somebody doesn't know, he is the person who is responsible for Ph.D. comics. I'm sure that a lot of grad students out there who are listening to this podcast, or even undergrads, know those comics. So yeah, he is responsible for those brilliant comics. Okay, so many guests have appeared on your podcast over the years, right? I mean, on your previous podcast and on your current podcast. Is there any particular guest that you really liked talking to?
Oh man, I had a lot of fun with basically everybody. Um, who's a guest I was particularly enjoy talking to? I really love talking to science fiction authors. I'm a huge reader of science fiction, and the podcast gives me the opportunity to write to these guys or ladies and get to talk to them and hear their stories. How did you become a writer? What's difficult? What's fun? How did you write this book? So for me, it's like fanboying a little bit. And so I got to talk to people I've looked up to for years, and I have an excuse to invite them on the podcast and talk to them about the science of their books. For example, Alistair Reynolds, he's a fantastic writer and a physicist. He used to work for ESA doing astrophysics and started writing and then transitioned to being a full-time writer. So that's a dream for a lot of people and a fantasy of mine to write science fiction. And so that's really fun. I got to talk to the writers of The Expanse recently. We had them on the show. So I was a little starstruck there, love that show. I love the hardcore physics in it. So really enjoyed that. I also like talking to very formal physicists. Talked to Thomas Van Riet recently about string theory, Jonathan Oppenheim about his post-quantum gravity, and asking them naive questions about formal theory. But I think one thing that's been really fun for me is giving me new questions to ask the theorists in my department. So if I'm preparing an episode on a topic and it's a little bit more theoretical than I'm totally comfortable with, I will go down the hall and I'll ask Tim Tate or Jonathan Fang or Arvind Rajaraman one of these questions like, hey, can you explain to me the intricacies of this question in quantum field theory? Because I want to make sure I really understand it before I explain it to people. Because because you explain things to people that to give an intuitive explanation of something, you have to understand it really deeply. Not just like mathematically, like, well, I can play with the equations on the page, but I get what this is so that you can give a satisfying, short, jargon-free answer. And that's been wonderful for me because they're great teachers. And so I've learned a lot of physics doing the podcast. And I go downstairs and I talk to the galaxy formation folks. And, there's questions in astrophysics I've always been curious about. How do we know the galaxies started out from baby galaxies and came together and didn't just collapse all as one? But it's not my particular area of physics, so I never had a reason to go and dig into it. And the podcast gives me a reason. And then I go and get an understanding of it. And so my knowledge of physics is so much broader and stronger than before the podcast. I don't think I've learned a lot of experimental particle physics on the podcast, but I've strengthened my knowledge in every other adjacent area dramatically, which has been great for me and for my science.
Right. It's interesting. I went through your podcast episodes, and I think I probably missed it. I didn't know about this Thomas Van Riet episode. I will check it out.
Oh, it's
Are you?
not out yet. We just had that conversation. It'll
Oh,
be out very soon. Yeah.
that makes sense. That makes sense because I was like, how did I miss it? Okay, so the thing is that there were a lot of big names in the in the 20th century, regarding science fiction,
Mhm.
like Isaac Asimov, like Douglas Adams, or like Arthur C.
Mhm.
Clarke. So if you could invite one of them to your podcast, who would you invite? Yeah.
Wow. What a question. Oh man. Asimov is up there for me. Foundation, I think, just was so influential on me as a young reader. I remember reading that and thinking, oh my gosh, he's actually doing science fiction, not technology fiction. Not here's a new gizmo, let's see how it changes what it's like to be human. Let's come up with a new science, right? His science of, historicity, I don't remember what the word for it is, of predicting large scale trends in human behavior. I thought that was so brilliant because it also taps into something which I think is really fascinating about science, that often we can find simple descriptions of emergent phenomena without understanding what's going on underneath. Like we're doing particle physics right now, you're doing quantum field theory without knowing what is quantum gravity. And you don't have to know, right? And the folks who do fluid dynamics, they can use Bernoulli's equation without knowing what the particles are doing or caring. So the fact that you can sometimes solve what seem like they should be impossible problems with fairly simple mathematics is an incredible thing about our universe. I don't know why it works. I think philosophers don't know why emergence is a thing. Um, and that book I thought was really brilliant because it tapped into that. It imagined a new level of emergence. Predicting the future of human behavior seems impossible. It's so chaotic. Yeah, well, but we can also predict lots of things that should be chaotic, like the flight of a baseball. In principle, could you model 10 to the 29 atoms and their movement through the atmosphere? It sounds impossible, right? You have to write the wave function for that. Well, you can use it F equals ma. The mathematics is shockingly simple. So I don't know if it'd be an interesting conversation, but I'm maybe most deeply impressed by Asimov as a writer because I think he really did create a new kind of potential science, a fictional science in his books, not just technology.
Right. Okay. So there's one question about science communication that I am a bit torn about. So the question is that what do you think about the role of humor in science communication? I mean, some people think that it's very important to engage audience. Some people think that they use a term which is a bit I don't know, it's a bit, I think it's a bit dated term, but it's called dumbing down. So do you think that that's necessary for communicating science, and putting too much humor in science communication is good for science communication or not? So what are your thoughts about using humor in science communication?
It's a great question and an important one. I think the answer is that it takes all kinds. You find people out there who want very serious conversations about science because they want to feel like they're being taken seriously and they are serious. And that's fine. There's place for that. But I think a lot of people find that unapproachable. And to me, the role of humor is to make science more approachable. We're not dumbing it down, we're making you comfortable. So, the reason I reached out to Jorge years ago to collaborate was because I saw in his comics that he was great at explaining stuff, but he's also great at, humor that was accessible. And so the first project I wanted to do with him was to make an explainer about dark matter and to have jokes in there, and to do a cartoon precisely because people don't find cartoons intimidating. You don't pick up a cartoon and be like, this is going to be too hard for me. The way somebody might pick up a book on quantum field theory and glance at the math and be like, well, this is a language I can never understand. The cartoons serve to make you feel like you can get this. This is not over your head. And I think humor in a podcast does the same thing. Hey, we're just people. We make jokes. We're having fun. And it also gives your brain a break. You just heard 5 minutes about quantum gravity. Okay, let's make a joke. And then everybody can relax for a minute and then sort of pull their thoughts together. It paces things. So I think humor serves an important role for lots of people, making them feel like it's accessible. It's a human thing. It's not too intense. In written work, I think it's really important for showing, for making it feel less intimidating. But there's definitely people who don't like it, and to each their own. And, just the same way some people like French cuisine and some people think Japanese food is the best, like we should have all kinds. So we should have very serious people who take themselves very seriously, and we should have people who make lots of silly puns,
Hmm.
because there's an appetite for all of it.
Right. So we're living in an era where there is too much misinformation on the internet. I mean, about almost everything,
Yeah.
and particularly about science. So in this particular era, doing good science communication is much more important than it was previously, I think. So the thing is that right now we have a big chunk of people who are either skeptical about science,
Mhm.
or they are intimidated by science. So it may be a very hard problem to solve, but what do you think, how should we engage these kind of people to come to science? People who are
Wow.
skeptical about science or people who are intimidated by science.
It's a great question, and I don't know the answer. I've been experimenting myself because I see that science misinformation is much more successful than science
Mhm.
communication. There are folks out there who have huge platforms who just spew nonsense, and I don't understand. I mean, I'm jealous. Like, how do you have such a huge platform? Like, what are you doing that I'm not doing that's attracting this audience? And I think that maybe what they're doing is tapping into people's anxiety or distrust, the same way, people you were mentioning earlier who communicate in bad faith, they get a big audience because there are people out there who want to hear, who want to take down the elites and the institutions, and they feel this anger, and it taps into a larger political movement. So there's a huge appetite for science misinformation, especially because a lot of these misinformation experts tell the same story. They tell the story that we were talking about earlier, like physicists are closed-minded and there's a mainstream narrative, and anything that's outside the narrative they shut down, and it's not really open, and blah 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 blah. um, I don't know what
Well,
to do about it. I've tried engaging with these folks directly. There's a guy on X, for example, who's a huge audience and is constantly claiming to be ignored by physicists. So I reached out to him. I was like, "Hey, physicist here. Let's
there
talk
are
about your
many
ideas.
there are
Send
many
me
people like
something."
that.
And he sent me something, and page one, first sentence. I'm like, I don't understand what this means. This doesn't make sense to me. And so I tried to engage in good faith, but I just got insults back. It's like, oh, you must be
Mhm.
an idiot, blah, 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 blah,
Yeah.
blah. I don't think they really want good faith engagement because it's bad faith smearing of science. So I don't know what to do about that. I just try to make myself available. I answer every email I get from every listener who writes to me, every crackpot who sends me a theory. I respond to all of them because that's all I can do to make people feel like, hey, we are accessible, we are open to ideas and contributions and to the general public, and we should be. But um, I don't know how to fight this problem of misinformation. It's a big, big problem.
Yeah. I think the problem is that misinformation in general finds a lot of audience. I mean, science communication, science misinformation is a part of it, of course, but misinformation in itself is
Yeah.
very harmful. And the examples that you were giving, the people who say that physicists are doing bad faith research. Okay, I think that's bad. But the thing is that okay, it's bad, but it's not a menace to society. I mean, I'm talking about people who are like vaccine deniers, who think that Earth is flat. Well, okay, even that is not that big of a problem. But if you think that, for example, 5G towers are giving you coronavirus, these kind of problems, I think they are a menace to society.
Mm.
And I think all of this has something to do with being extra skeptical of science and just not believing what scientists are telling you. Um, so I don't know how to engage with these people either. As you were saying, a lot of people, there were actually a lot of people on Twitter or X who claim to be ignored by physicists, and I have done probably more than my fair share of engaging with these kind of people, and many a times I just get insults back. But the thing is that there was this story that I didn't know about. I recently learned this story. So there was this. So you are a member of American Physical Society, right? So when American Physical Society has a meeting, there is this crackpot session that also goes on, right? And I didn't know why that's the case, but then I learned about the story that there was this crackpot who killed a girl in American Physical Society building in
Oh.
the early 50s. And the reason why he did that is that he sent them a paper and they didn't publish it. And he said that, yeah, okay, you are ignoring me. So he went to the, APS building somewhere and, shot the first person who he saw. And it was a girl.
Mhm.
I think it happened in 51, I think. So after that incident, they allowed, this crackpot session to happen if you pay a fee. So they can go to that extent as well. I mean, they will not just insult you; they can actually kill you if they think that you are just ignoring them. So that's I don't know how to even make sense of this. That they're that indulged in this particular idea that their ideas are just being ignored by physicists. So I think it's a bigger problem than meets the eye. So
And I
again,
think there's lots of different people in that community. There are people who are sincerely interested in physics and want to make a contribution and have done something they think is worthwhile and just want somebody to look at it. And that's good faith, right?
yes.
Non-expert, good faith engagement. And people send me that stuff and I read them and oh, here's a mistake, or you forgot this, or you might not know about this, or whatever. And that's fine. That's great. But yeah,
Hmm.
there's a lot of people who are doing it, I think, in bad faith. There's one guy on X, for example, believes that cold fusion is real and that the government is hiding it.
Yeah.
And also we can extract energy from, the quantum vacuum. And also the wormholes ate the Malaysian flight and the government is hiding that technology. It's just like this soup of nonsense with no science behind it, but with a massive audience. And so I think you're right that it's the larger problem of misinformation is that it's telling people something they want to hear. They
Mm.
want to hear that the government is lying to them and scientists are idiots or scientists are a conspiracy or something. And why do they want to hear that? Because there's something they're dissatisfied in their world. I don't know. I'm certainly not an expert
Hmm.
in that. And I don't know how to solve that problem. But it is a big problem if, as a society, we have no shared upon a way to establish what are facts, right? We have no institutions we trust where we can say, oh, look, blah, 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 establish these things. Let's start from there and talk about policy, whether it's public health or funding. Say, for example, an asteroid is coming towards the Earth. If scientists have no credibility, there's no institution of scientists that's broadly believed and trusted, how are we going to advise the government about the options for what to do to save humanity? Like, it is a big problem if science itself loses its credibility.
Yeah. I
And I
mean,
think these bad faith engagements are really damaging that way.
Yeah, as you said that, I mean, we don't know what's the reason for them believing these kind of stuff. But one of the things can be that they are just dissatisfied by something in their life. I can tell you that scientists are dissatisfied so by many things in their life as well.
Yeah,
But we don't,
it's true.
we don't go to these kind of conspiracy theories. I
Hmm.
mean, as a graduate student, you're paid like very a small amount of money. But, so
Yeah.
we are dissatisfied, but the remedy is not to go to conspiracy theories. I mean, well, I can say that there is some, body that has conspired against grad students to pay them less. That's not going to solve anything, of course, right? Okay. So, okay, three questions, and then I have some people's questions, and then we can wrap it up. So,
Okay.
one question is that how do you balance your time in popular science and research?
Yeah, that's a great question. And in general, the people struggle with how to balance their time just as a as a scientist or as a professor. You have lots of demands on your time: service work, teaching, research, home life. Adding popular science communication is a challenge to that. I mean, I write books, I do the podcast, I do the TV show. It's not a trivial amount of time. My guideline is I do what's fun. And so there's too much to do, but I try to focus on the parts I enjoy because those are the things I'm going to do well. So I don't sign up to do things I don't think are going to be fun because I don't think I'm going to do a good job at them. And so I think every day, what am I going to have fun doing today? And I try to put some creative energy into that. And some days I have a lot of energy for science communication, prepare a bunch of podcast episodes, work on a new book proposal. Um, and some days I'm like burnt out on that, and I just want to dig into the code of some project I'm working on and make some plots. So I don't have like a magic recipe for how to balance stuff. I just try to make sure I'm working on stuff that's fun. And I give the same advice to young researchers, my grad students and my postdocs. Say, make sure you're always working on something exciting. Don't work on something that is boring and frustrating because you think it's going to have some big career payoff later on. Make sure you're doing something fun because you're going to be doing your best work. I want them working on things where they're thinking about it while they watch Game of Thrones, or they have an idea in the shower and they're writing it on, in in Steam on the shower wall or whatever, because it's something that's captured their energy. So I try to do that as much as possible. But
Um,
it's a real challenge for early career folks to do science communication. I asked some folks like Sean Carroll and Stephen Strogatz if they would advise young folks to do science communication, and broadly their advice was no.
yeah, I know.
Focus on your research and then later on broaden. And it's not fair, and it's ridiculous, but a lot of people see science communication negatively in the field. As Sean Carroll says, if you have some weird hobby, like you ride a unicycle, everybody thinks that's quirky and fine. But if your hobby is science related, people think, why are you doing that? You should be doing science instead. And so it's not a fair criticism, but it's just sort of part of the way our field is currently. And I
Um,
think it's changing and improving. I hope so. Um, but
yeah,
it's delicate for young people.
I sometimes think that I may have given too much time to science communication. I should have, I mean, I have given time to my PhD, of course, but I think sometimes I think that I should have given more time.
Yeah.
Yeah, so that's something that lives in my mind, and I think it happens because how the field is structured. If you are, a young researcher, I think it will be a bit more, I don't know how to say this, harmful for you if you give too much time to science
Mhm.
communication and not to your research. I mean, if you want to, not do research after your PhD, I think then it should probably be fine. But if you want to be an academic after your PhD, then it's a bit harmful to do too much to do too much science communication. Okay, so what criteria do you follow, or what criteria do you have before you accept a PhD student?
Oh, wow. Wow, great question. I look for students who are deeply self-motivated. They have a question they want an answer to. I don't want students who just want to execute a part of my research program because I don't want to drag anybody across the finish line. I want them to be excited. I want them to be having fun. I want them to be emotional about the answer to their question. And so I want the question in the end come from them, to be connected to them. Um, and I look for students who are independent, like not in the way that they already know everything or they never need to ask questions, but that they want to find the answers themselves and they want to learn to be an independent researcher. Because I see graduate students as needing to learn how to be researchers, and they come out of undergrad being homework machines. Like they can do problem sets like crazy, but they don't know how to do research broadly. And so I'm looking for students who have that interest in actually becoming independent researchers. It's not always easy to spot, but that's what I'm looking for. Students who want to be learn to be independent rather than micromanaged, and students who really have a deep motivation to answer a question themselves.
So another question is that how to deal with failure or failures as an academic.
Get used to it because it's more common than success. Um, and you have to tell yourself that the process is largely random, or it's a huge random component, which means that when you win, you get a grant or you get a job, there's a lot of it was just random. And when you lose, you don't get your grant funded and you don't get that job, a lot of that is random. The process is hugely imperfect, right? It's not a meritocracy. There's relationships. People are doing their best to try to guess who's going to do the best, who should get the money and who should get the job. But it's hugely, hugely imperfect. So that helps me. And, have lots of things in the fire. So, yeah, that proposal didn't go, but you got five more. And so one of them is going to go. Um, so that's how I deal with it. But mostly you just get used to it and you accept that it's part of the job is coming up with all these great ideas and then not getting to do them.
Sure, sure, sure. Okay. I think what you are talking about is rejection, right? Rejection from a job or rejection from funding. I'm talking about when a project fails, a project that you have been working on for 1 year or 2 year fails, then how to get back from that?
Yeah, that's tricky. Um, I think that you can structure your research to minimize that because you can organize your projects in a way that the answer is interesting no matter what happens. It's hard to talk about it in a very abstract way. But when I'm designing projects for young graduate students, for example, I try to pick projects so that the answer is interesting either way. For example, um, you know, let's try to do this new hard thing. If it turns out we can do it, awesome. That's obviously interesting. We can publish it. If it turns out that we can't, let's have our approach be systematic enough that it's interesting that this is hard, that these ideas you thought might work don't work, and we can learn something about the problem by having failed. In experimental particle physics, we publish whether we see the particle or not. So, like, oh, we didn't see this, we set limits. But more broadly, I want to make sure that we're going to learn something either way. So, it's pretty rare that we have to throw away a whole year or two of research. That only happens if there's been a mistake. Like, okay, we saw this early result, and then we doubled down, we dug into it for a year or two, and then turns out, oops, that was a bug. And this whole thing was a waste of time. That you can avoid mostly by having, sanity checks. Let's double check. Let's make sure this makes sense. Let's come at it from another perspective. Just to convince yourself that something is real and rather than an artifact. So it's been pretty rare to have a project fail. I did have one project fail for political reasons, which is I spent a year or two on a project. It was a year and a half as a postdoc. This was really painful on a project, and then got scooped by somebody in my own collaboration. I used to work on a CDF collaboration, and that place was a shark tank. You could be working on something, and then somebody else just swoops in. Oh, I've been working on this in secret for the last year and a half and haven't been presenting at all. And boom, um, and got scooped and pushed out of that project politically. That was pretty painful. I just about decided that I was done with particle physics and my postdoc was unsalvageable. My wife convinced me not to give up, and I turned around and started a new project, and that worked out, and I ended up getting a faculty position based on that. But um,
But how did you console yourself in that particular time?
I told myself that I'd done something interesting and I'd done it once, I could do it again. And so I thought to myself, all right, I've got a year or so left before I have to really produce something interesting in this postdoc. What can I get done in a year? And that's really the challenge of science. Is not like, what's a question that's fun to answer? That's not hard to think about. It's what's a question that's fun to answer that we might be able to say something interesting about within 12 months, given the resources we have. That's the challenge of science, right?
And that
Coming
nobody
up,
else is working on
and
that.
that nobody else is working on.
Yes.
Identifying those bite-sized pieces of science, that's the really hard problem in being a scientist. And I said, well, okay, I did it once and I could do it again. And so um, let's go. And I have this job, and I might as well give it another try. I had a 3-year appointment, and I was a year in, and so I thought I got one more try. I'm not going to give up. So credit to my wife for encouraging me to keep going, and I did, and it all worked out, and I got a faculty job, and I'm happy that I stuck with it.
Okay, great. So I have some people's questions. I think I have 5 questions.
Okay,
Three
cool.
of those, three of those questions have already been answered, I think, in our conversation. So let me just take the two questions which were not answered. So one question is that uh, how might upcoming upgrades to the LHC and detectors help you in getting, some new discoveries or answer some exciting questions?
Yeah, great question. The upcoming runs to the LHC are going to be mostly running longer, running with more collisions per second to accumulate larger data sets so we can answer questions with high precision that we couldn't answer before, measure Higgs properties, et cetera, et cetera. But I think that's something that's overlooked is that we also have very high fidelity in these detectors. And I'm actually more excited about reanalyzing the older data where we had fewer collisions per second to look for things like quirks that are hidden in that data. So I'm more excited about thinking about ways we haven't yet looked at the data than actually I am about gathering more data. Um, I'm less bullish on gathering more data quickly than I am about figuring out clever ways to examine the data we haven't thought about yet, honestly.
Oh, actually, we have more than 2 questions. So one question is that, do you think that sometime in the future we will build a particle accelerator on the moon?
I love this idea. Excuse me. I absolutely love this idea. I do not think we're going to build a particle accelerator on the moon. Everything in space is harder than it is on Earth. Oh my gosh. Like unless you could somehow build it with materials you find there, but then you need a whole infrastructure and supply chain and industry on the moon. But if you're launching stuff from Earth, man, and then supporting it from Earth, it's just impractical. I think it's ridiculous, but I think it's a wonderful idea to think about, and it's fun, and it's a great example of just like creative out of the box thinking. But no,
Yeah,
I don't think we're building it.
I mean, for example, if we try to build a particle accelerator on the equator, we do know that we have oceans to deal with, but that's not a problem on Moon. So we can
Right.
build a particle accelerator on the circumference of the Moon, which will be huge, I guess.
Yeah.
Um,
But you have to deal with the power, right? And solar power, and you don't, and the moon, the cycle there is very strange. You have to bury it under the regolith. There's a lot of things to deal with if you're going to
yeah,
build a particle accelerator on the moon.
and I don't know that the absence of atmosphere on the Moon, will that be a huge concern or not? Because cosmic rays can, you
Mhm.
know, come in the accelerator. I don't know if that's a huge concern or not. Is it a huge concern?
Well, it's a significant background to your detectors for sure, right?
Mhm.
Um, so you may want to bury it under regolith also
I
because
see.
it is safer, right? You can't exist on the surface of the moon without significant radiation shielding anyway. So,
Right, that makes sense. Okay.
and the surface of the moon, the temperature changes are dramatic,
Hmm.
huge swings. And so you probably want to bury it because you have sensitive equipment. You don't want hundreds of degrees of temperature change on a regular basis.
I see. I see. Okay. One more question. So
Hmm.
please don't take it as some hard criticism. It's just a light-hearted question.
Oh
So
boy.
I think it's just a light-hearted question. The question is that you have written a book with Jorge Cham named "We
Hmm.
Have No Idea."
Mhm.
which is about things that we don't understand in physics. So, do you think that the title of this book can be used by science deniers?
No, I think the title of the book is there to convince folks that scientists have humility, that we don't claim to understand everything, because I think that's the major criticism of science deniers. Physicists say they know everything, but no, we don't. We admit we have no idea that most of science is to be figured out. There are open questions everywhere. So I certainly hope not. But I think everything can be taken in bad faith
Yeah.
by misinformation merchants. But yeah, the goal of the book was to encourage people to understand that we don't know everything in the universe. There's still a lot to figure out, um, and and that's supposed to inspire humility and excitement about the future.
Okay. So we have kind of addressed this question, but if you want to say anything about this question, you can. So, what's his view on public outreach for high energy physics, which is regularly accused of ivory tower science and lacking any practical use?
I don't think that science needs obvious practical use to be worthwhile.
I agree.
I think that investment in basic research is the most obvious good investment we can make, no matter what your motivation is. If you're a philosopher or a pure scientist, you just want to know how the world works, cool. Let's buy some knowledge. Like the thing that limits our knowledge of the universe is just money. We can just purchase knowledge about the universe. We can build more space telescopes, more colliders, and just buy knowledge. Like it's really just there for us to purchase. And we keep buying other things. Like, how much money is spent by humans on cell phones every year? Like, it's staggering how much money we spend on trivial crap that we don't spend on deeply important issues.
I
But
mean,
even if
and
that's not important,
cell phones are made because of quantum mechanics,
yeah,
which
exactly,
was
right?
made in the 20s.
And even if that's not important to you, if your issue is economics, like what's a
Mhm.
better investment than basic research? Now, not in 1 year, not in 5 years, not guaranteed in 20 years, but in the long term, you want to invest in your society? Basic research. If your issue is military hegemony, you want to, make sure America has the greatest military. Invest in basic research. That's the way to do it. Physics will deliver, I promise you. If your issue is cultural power, like invest in basic research. The smartest people will come to your universities. You be the center of the world. Like, I don't get it. I don't know why it's not bipartisan. Republicans should love it. Democrats should love it. Everybody should love it. I don't know why we're not have 10 times the research budget than we do today. It's nonsense to me. So what do I say to people who think physics is ivory tower and has no practical use? I think that investment in physics is good for everybody, and I don't understand why more people aren't excited about it.
Okay, so I think my questions are over. Thank you so
All
much
right.
for your time. It was great talking to you
Thank you very
regarding many things.
much. Yeah, and your wonderful conversation list. I haven't seen your earliest episodes, but I think you do a great job keeping a conversation going. It was a lot of fun.
Thank you. Thank you so much for your time.
Thank you.
And probably we'll talk again, sometime regarding other things as well. So
Absolutely. Great.
thank you.
Thank you.
Thank you. Have a good day. So if you like this video, give it a thumbs up and consider subscribing. And the YouTube algorithm thinks that you will also like this video.